Hello everyone. Today I will discuss Euler's equation of motion, which is very commonly used in fluid dynamics, and from this equation we will derive Bernoulli's equation. Consider a small fluid element in three-dimensional fluid flow, as I am drawing here. This fluid element is a parallelopiped, or you can say it is a rectangular block, as shown here. Now let us say this face is P, Q, R, S, and this face on right hand side is named as P dash, Q dash, R dash, S dash. Here it's a very small parallelopiped element, and dimensions of this fluid element are: length is delta x, length along y-axis is delta y, and height is delta z, which is along z direction. First of all, consider the left hand side face and say P is the pressure intensity acting on this face. So P is the pressure at P, Q, R, S face. It is along x-axis. Now, if you want to obtain the force on this face, we can get it by multiplying pressure with area, and area of this particular face is delta y into delta z. So it is clear from the diagram. Now force will be equal to P into delta y delta z. So I can write it here only. So this is the force acting on this face. Similarly, we will have pressure on the right hand side face, on this face. And suppose P dash is the intensity here. Now what is P dash? Mathematically we can express it like this: P plus del P by del x into delta x. Why do we express it like this? Because this particular term del P by del x is a rate of change in P, that is pressure intensity, along x-axis. So therefore, after a distance from this face, left hand side face, to right hand side face, after a distance of delta x, change in pressure should be rate of change in pressure into distance. So this is a change in pressure intensity, and we add this particular change here to the pressure on left hand side. So therefore, force on right hand side face, which is P dash, Q dash, R dash, S dash, that will be obviously P dash into area. Area is again delta y into delta z for this face also. It is clear. This area is delta y into delta z. So we can write it like this: P plus del P by P plus del P by del x into delta x into delta y delta z. Now in Eulers equation of motion, we have two types of forces acting on the fluid, and these are pressure force and body force. Pressure force is due to head differences or due to flowability of liquids, and body force, they come from such as gravity or magnetism, etc. So in this particular case, pressure force will come from this pressure intensity and body force will come from gravity, or there can be some other sources of body force. Now let us say x, y and z be the body forces along x, y and z axis per unit mass of fluid. So that means body force along x-axis would be how much? It will simply be x into mass of element. So you multiply intensity of body force x with the mass. Mass of the element is density into volume. Density is rho. Rho is density, which is mass density in fact. Rho into delta x, delta y, delta z. So we multiply volume with density and we multiply this mass with intensity of force per unit mass. We get the total force acting on the element along x direction. Now in this particular element, if you see along x-axis, only x-axis, we have three forces acting. One is due to pressure P, other is due to pressure P dash, and other is body force X into rho delta X, delta Y, delta Z. Now what is the net force acting along X direction in this particular case? The net force acting along x direction, and that is P into delta y, delta z, it is acting towards right, minus P dash, which is P plus del P by del x into delta x multiplied by delta y, delta z, that has already been obtained. This is acting towards left, plus body force, which is x into rho delta x, delta y, delta z. Now this net force should be equal to mass into acceleration of fluid element in x direction as per Newton's second law. So this is the net force and it must be equal to mass into acceleration. It is as per Newton's second law. And we can write it like this: mass of this block element is rho into delta x, delta y, delta z. Acceleration in x direction is ax. So if we compare these two forces, we will get P into delta y, delta z minus P plus del P by del x into delta x into delta y, delta z plus x into rho delta x, delta y, delta z is equal to this mass into acceleration expression, rho into delta x delta y delta z into ax. This term is struck off here, and we get these also struck off, they're also gone. So we are left with minus del p by del x plus rho into x is equal to rho into ax. So in simple terms we can write it like this: x minus 1 by rho del p by del x is equal to ax. So this is one of the equations, equation 3. And similarly for y direction and z direction we can write the equations like this: y minus 1 by rho del p by del y, it will be equal to ay, which is acceleration in y direction. And for z we will have z minus 1 by rho del p by del z, it will be equal to az, which is acceleration along x direction. So we have these three equations. These equations are called as Euler's equation of motion. So we have derived this. Now we can also express these equations in terms of velocity. So how do we express this equation in terms of velocity? So as we know, acceleration in x direction ax is given by del u by del t plus u del u by del x plus v del u by del y plus w into del u by del z. Similarly we have ay and az. Ay will be del u by del t plus u del v by del x plus v del v by del y plus w del v by del z, and az would be del w by del t plus u del w by del x plus v del w by del y plus w into del w by del z. So as we know, these three components, they are called as local acceleration components in fluid, and the rest of the components which are in terms of space, they are called as convective components, convective acceleration. We can substitute these components back into Euler's equation. Therefore, the first equation will become x minus 1 by rho into del p by del x. It will be equal to ax. Ax is, we have here as it is, that will come here. This entire expression of ax will come here. Similarly, for ay, we will have x minus y minus 1 by rho into del p by del y is equal to ay. And lastly, we will have z minus 1 by rho del p by del y, it is equal to az. So we will have these individual expressions right here, and this will be here, and the last expression of az will come here. So that's all. So we have finished with Euler's equation. Now next part of this discussion is derivation of Bernoulli's equation from these equations. How to derive or obtain Bernoulli's equation from Euler's equation. Now we will discuss how to derive Bernoulli's equation from the Euler's equation that has been derived previously. So for that, let us assume that there is a force potential which is omega, whose negative derivative with respect to any direction, whose negative derivative with respect to any direction gives the body force in that direction. So if I differentiate omega, which is force potential, with respect to x and take its negative, this will be x. And what is x? It is body force per unit mass. Similarly, if I differentiate omega with respect to y, it is negative derivative again, it is y. It is body force per unit area, per unit mass in x direction. This is in x direction and this is in y direction. Similarly, negative derivative of omega with respect to z will be z, capital Z, which is body force per unit mass in z direction. Now, if the flow is irrotational, that means omega x, omega z, omega y, they will all be 0. So due to that, we will get del u by del y is equal to del v by del x, and del u by del z is equal to del w by del x. Omega x, if I take, we know that it is given by half del w by del y minus del v by del z. And if it's 0, if this is 0, we will get del w by del y is equal to del v by del z. Similarly, omega z is equal to 0, that means half of del v by del x minus del u by del y will be 0. That will give us del v by del x is equal to del u by del y. So all these are angular velocities. So their units are radians per second. This has been obtained by taking omega z equal to 0. This is obtained from omega y equal to 0, and this is obtained from omega x is equal to 0. So since the flow is irrotational, therefore angular velocities will be 0. If we move further, we will have this relationship for expressing u, negative of del phi by del x, where phi is velocity potential. Well, we know the definition of velocity potential. that its negative derivative with respect to any direction will give the component of velocity in that direction. So we are right now working for x direction. So same will be valid for other directions also. Now differentiate this with respect to time. So we will get del u by del t equals to del y del t of minus del phi by del x. So this can also be written as del square phi by del t del x, negative sign. This can also be written as del square phi by del x del t. Means we can switch the order of differentiation. Well, that is possible if phi is a continuous function. Apart from this, it should also be true that second derivative of phi should exist. It should exist. So substitute these equations into Euler's equation. Euler's equation in x direction was x minus 1 by rho del p by del x is equal to ax, and ax was del u by del t plus u del u by del x plus v del u by del y plus w del u by del z. If we replace the velocities in terms of phi, so this can be substituted here in this equation. So therefore we get here, and also this body force was differentiation of omega with respect to x, negative differentiation. So therefore the new equation will be minus del omega by del x minus 1 by rho into del p by del x is equal to, start from here, del u by del t was obtained to be del square phi by, well, negative of it, del square phi by del t del x plus u del u by del x plus v del u by del y plus w del u by del z. So now what can we do? We can also replace del v by del y and del u by del z in terms of differentiation with respect to x to match it with this one. So from the irrotational flow conditions, we can easily get that this is equal to del v by del x, and this is equal to del u by del z is equal to del w by del x. So these have been obtained from here. So just replace them, and Euler's equation will be modified to this as I'm writing right now. Therefore we get it to be minus del omega by del x minus 1 by rho del p by del x is equal to del square phi by del t del x plus u del u by del x plus v del v by del x plus w into del w by del x. Now we can shift these u, v and w under the sign of differentiation, and we can write them like this: minus del square phi by del t del x plus, we can write it like this, del u by del x of u square but divided by 2. Similarly, this can be written as del by del x of v square by 2 plus half into del square of w square by del x. So this simply has come from here. If we have half u square and differentiate it, we should get u. So we have just brought u, v and w within the purview of differentiation. Now we can carry this left hand side term to the right and we get the final equation looking like this: del by del x of omega plus p by rho plus u square by 2 plus v square by 2 plus w square by 2 minus del phi by del t, it is equal to 0. So we have easily taken the common del by del x from all the terms. Well, this will be only single differentiation. Now, if flow is incompressible, that simply means rho is constant, that is density, mass density of the fluid is constant. In that case, p by rho will also be a constant. We can now integrate this particular equation with respect to x. So what do we get here? After differentiation, we get omega plus p by rho plus u square plus v square plus w square by 2 minus del phi by del t, and it should be equal to some function of y, z and t. This can be a function of y, z and t, because when we will differentiate it with respect to x partially, we will get 0. So this is after integration with respect to x, where f1 is an arbitrary function whose value can be obtained from boundary conditions. Now, if the fluid is compressible, if the flow is compressible or fluid is capable of changing its volume under pressure, then what happens? Then rho, that is density, depends upon pressure. So pressure will change density because it will change volume. Mass will remain constant, therefore density will change. So in that case, integration with respect to x of the original equation, this equation in this case will give us a new equation, and that can be written as omega plus integration of dp by rho. This is due to the fact that p affects rho, plus u square plus v square plus w square by 2 minus del phi by del t is equal to function of y, z and t. T is time here. Here also we know u square plus v square plus w square can be written as capital V square, where v is velocity of the element which is being considered here, of the fluid element, and u, v, w are obviously the x and y and z components of this velocity. Similarly, For y direction, this equation can be written as omega plus integration dp by rho plus v square by 2 minus del phi by del t is equal to some other function of x, z and t. This time we have x, z and t, not y. And for z direction, we can write omega plus integration dp by rho plus v square by 2 minus del phi by del t is equal to some other function f3 of x, y and t, not z. So this is v. The first equation is for x direction, y direction, z direction. Now if you observe these three equations, so I'll rewrite equation for x direction. Omega plus integration dp by rho plus v square by t minus del phi by del t is equal to f1 of y, z and t, function of these. So among these three equations, the left hand side are same. So that simply means f1 is equal to f2 is equal to f3. So they should all be same. They should be independent of space. It is constant. Now we can write these constant to be ft, function of time, a single function of time. They are all same, and we can say that omega plus integration dp by rho plus v square by 2 minus del phi by del t is equal to ft, which is same as these. This is called as a pressure equation. Now for steady flow, we know del phi by del t should be 0, because steady flow is the one when properties of flow do not depend upon time. So differentiation of phi velocity function should be 0. So this equation reduces to omega plus integration dp by rho plus v square by 2 is equal to some constant. This is a constant, because now nothing depends upon time, so this will also be a constant. Ft is simply f, or some constant. Because it is also not depending upon time. Let us focus on omega. If only gravity forces are acting, only gravity is there is no other body force, then in the Cartesian system here only g is acceleration due to gravity acting downward. So as per the definition of omega, minus del omega by del x should be 0, because there is no body force along x direction. Similarly, negative of del omega by del y should also be 0. There is no gravity along z or y direction. But when we differentiate it with respect to z, del omega by del z should give us minus g. Minus is because z axis is upward, and g, if we take upward, it should be minus g, because this is acceleration due to gravity, which is downward actually, so it has to be negative. Now if you integrate this, integrate with respect to z, what should we get? We will get here omega is equal to g into z plus some constant c1. Well, we could have written it as del omega by del z is equal to g. So from there we can differentiate it to get omega is equal to gz plus c1. c1 is some constant. And how can we get this constant? Like this, at z equal to 0, omega is 0. Obviously. Therefore, if this is 0, this is 0, what we get? c1 comes out to be 0. So therefore omega is equal to g into z. Therefore the equation that we have just derived now becomes integration dp by rho plus v square by 2 plus omega, which is dgz, that is equal to some c constant. And this equation is known as Bernoulli's equation. So this is how we derive it. Now we can go for simpler cases, like when we have incompressible flow. Or incompressible fluid. We know rho does not depend upon pressure, that is P. So therefore integration of dP by rho will simply be P by rho. So this equation becomes P by rho plus V square by 2 plus gz is equal to c. Now divide throughout by g, P by rho g plus V square by 2g plus z is equal to c by g. And c by g is again another constant c dash, so we can write it c dash, and so this becomes Bernoulli's equation for steady and incompressible flow. Now moving further, rho into g is W, which is specific weight of fluid. So we can write it like P by W plus V square by 2g plus z is equal to c dash. So this is equation in terms of weight. Now here, what is PW? They have got separate names. P by W is called as pressure head. So in this equation, every term will have unit of distance. They will be in meters or centimeters or feet or millimeters. So that is called as head in terms of water height. Pressure head. Second term is called as velocity or kinetic head. And Z is called as potential head. Z is called as potential head. or it is also called as datum head. Now P by W plus Z plus V square by 2Z is equal to C dash. This is another way to write it. We can combine P by W plus Z. These two together, that is called as piezometric head. If we add pressure head and datum head, they are together known as piezometric head. Now for any flow, if this goes up, if velocity goes up, then to maintain this as a constant, this has to go down, and vice versa. If velocity goes down, pressure head or piezometric head will go up. So therefore, whenever in a pipeline, when velocity increases due to some reason, due to some blockage or something, velocity will increase. So at that point, pressure will drop, pressure head will drop, so that this expression remains valid, Bernoulli's equation remains valid. Now for a flow in pipe, we can have two sections, 1 and 2 for study. So according to this theorem, P1 by W plus V1 square by 2Z plus Z1 must be equal to the same thing for section 2, P2 by W plus V2 square by 2Z plus Z2. Since it is a constant, so these two expressions must be same for two sections. Now here Z gives the height of the section 1 with respect to some data. This height is Z1 and this height is Z2. If these two are at same levels, then Z1 will be equal to Z2 for 2 points being considered at being at same levels. So therefore these can be struck off and we can get simpler expression. V1 square by 2Z is equal to P2 by W plus V2 square by 2Z. V1 and V2 are velocity of flow at section 1 and section 2 respectively. Now this equation is valid, or even this equation is valid for no energy losses in flow. That is not a practical case. Practically, there are definitely some losses, and let HL be the head loss in flow due to certain factors. These factors can be like friction between liquid and walls of the pipe, or sudden bends in the pipe due to formation of turbulence, eddies, vortices, etc. There can be some pipe fittings which are blocking the flow at some places. So sometimes there is heat generation due to high velocity, and let us say that loss is HL. In that case, Bernoulli's equation can be expressed as P1 by W plus V1 square by 2Z plus Z1 will be equal to P2 square by W, it should be P2 only, P2 by W plus V2 square by 2g plus z2. This time, due to loss of energy, this head is lower than this head. So to compensate this inequality, we add here the loss. So we get this to be the equation. For the case when head loss is there. So head loss is added on the right hand side, because at section 1 energy is head is higher, at section 2 head is lower. So that is of course lower because HL is the head that has been lost due to flow or due to friction losses or due to some other minor losses. So this is how we derive Bernoulli's equation from Euler's equation. Thank you for your patience.